All right, welcome everyone to this month's Astronomy on Tap. My name is Alex Green. I'm a first-year grad student in the astronomy department. Our speaker this evening is Professor Yoni Kahn, an assistant professor of physics at the University of Illinois. He's a theoretical physicist whose research focuses on dark matter. He manages to work well with experimental physicists colleagues despite not being able to assemble Ikea furniture. This month, Professor Kahn will talk about the search for dark matter deep under a mountain in Italy and in an abandoned gold mine in South Dakota. The hunt for dark matter is on. He will explain how some of these experiments work and what's involved in designing new ones. So, Professor Kahn, you can take it away.
Thanks so much, Alex. Well, it's really nice to be here talking to you all. In ordinary times, we'd be doing this at a bar, but I figured that, during these pandemic times, the least I can do is fix myself a drink. So I've got my favorite drink, which is a Rye Manhattan. So I hope you're all following along with your own beverage of choice. So let me go ahead and share my screen. Okay, so my talk is called Things That Go Bump in the Night, or How to Search for Dark Matter. So the first thing I want to tell you is, what is dark matter anyway? Those of you that follow popular science, you might have seen some articles in the news recently about dark matter. So let me explain a little bit about how we think of it as particle physics. So 380,000 years after the Big Bang, the universe took a selfie, by which I mean that light left over after the Big Bang has basically been streaming towards us unimpeded for the age of the universe minus the 380,000 years. And you can actually go and, with very, very sensitive telescopes, make a map of that light. And it looks like this. So the way to interpret a picture like this is kind of like a projection of a spherical surface. So you can imagine a map of the Earth overlaid on this elliptical thing. And you'd see North America over here, and you'd see Europe and Asia over there. And so basically what it says is that go in any direction, point your finger any direction on the sky, and a point on this plot corresponds to a direction that your finger is pointing. So you can go around in any direction, and that'll be the temperature difference from the average at that direction in the sky. And so what you can notice is that there's some hot spots that are colored in red, and there are cold spots that are colored in blue. So some parts of the universe are hotter than others, and some parts are colder than others. So when I talk about hot and cold, what do I actually mean? So it's temperature, but the temperature of what? And the thing that measures the temperature of the universe is particles of light, which we call photons. So, if you talk about the temperature of an object, if you go and look at something with an infrared camera, what you're really doing is you're measuring the average energy of light coming off of that object, and objects that are at room temperature will radiate photons at a certain temperature. So it's really like looking at the universe, if you like, with something kind of like an infrared camera. Okay, so let's look a little bit more closely at this graph. So if you kind of zoom in on a section and you look closely, you'll notice that most of the hot spots and the cold spots have a typical size. You kind of squint and stare at this, you'll see that most of those little blobs are roughly about the same size. They're kind of distributed randomly, but most of them are roughly about the same diameter. So it's a little bit of a journey from that observation to the consequence of basically the statistics of these spots, how many of these hot and cold spots there are and what their average size is, turns out to be a telltale sign of dark matter. And that's true because basically the universe after the Big Bang is expanding really, really fast. And there's a competition between the expansion of the universe and the fact that if there's stuff there that feels the force of gravity, it's going to want to make it contract again. So that competition between expansion and contraction depends on the amount of stuff in the universe. And in particular, it depends on the amount of stuff that does or doesn't interact with light, which is the thing that is basically sensing that temperature. So dark matter for me means that it's something in the universe that carries mass, that if you put it on a scale, it will weigh something, but it doesn't interact with light. And I'm going to use the words light and photon interchangeably. So as particle physicists, everything is particles if you look down carefully enough. So the individual particles of light are called photons. And so that's how I'll describe it. Okay, so I just told you that dark matter doesn't interact with photons. So how can we see something that's dark? So the way that we see things in general, literally the way that your eyes work, is photons bounce off objects, and those photons then bounce into your eye. So for example, some photon, some particle of light might have been emitted from the sun. It might bounce off of a tree, and then that particular photon will bounce into your eye, and that's how you see the fact that a tree is there. So how would this process work if you had something that didn't actually interact with particles of light, such as dark matter? Okay, so to set the stage, let's imagine a game of catch. And it's actually a very unfortunate game of catch for you, because the thing that you're catching is not a baseball, but a cannonball. So let's imagine what happens. Somebody either throws or fires a cannonball at you. You're standing right there. What's going to happen? Well, you don't have to think too hard to realize that you are going to get knocked over. So the cannonball might bounce off you and go flying in some other direction, but almost certainly you are going to get knocked over by that cannonball if it's moving at any kind of reasonable velocity. And actually, Newtonian physics tells you why that's the case. So the typical mass of a human is 60 kilograms. Okay, I'm going to use the metric system because I'm a scientist, and so I'm kind of contractually obliged to do everything in the metric system. The mass of a cannonball, it varies depending on what kind of cannonball, but about the same order of magnitude, let's say 50 kilograms. So Newtonian physics tells you that if you have two objects that have similar masses, when they bounce off each other, they usually transfer most of the kinetic energy, the energy of motion of one object to the other. So the reason why the cannonball knocks you over is because it weighs about as much as you do. Okay, so with that in mind, let's do the same game, or let's perform the same experiment in the dark. What happens? So maybe now you can't see the cannonball, but you're definitely still going to get knocked over. So in this kind of cartoon analogy, you are a perfectly good cannonball detector. Even though the cannonball is dark, you're not literally seeing it with your eyes, but if you stand there and wait for yourself to get knocked over, then you know that a cannonball was coming and flying at you. And the reason this works is because there's a force between you and the cannonball that lets it transfer its energy. So I'm going to use the word kinetic energy, which is just the energy of motion. So, objects that are moving with a velocity can be thought to be carrying some amount of energy. And that energy, when it hits you, can do all kinds of things. It can give you bruises. It can break your bones. But the point is that there's some force between you and the cannonball that lets that transfer of energy happen. Okay, so with that analogy in mind, dark matter is like a barrage of cannonballs, or a barrage of some other kinds of objects that have a different mass. So let me talk about the difference between cannonballs and ping pong balls. So if dark matter particles actually weighed as much as a cannonball, it would be very easy to detect them. You can actually go and calculate what the number of dark matter particles would be that would be hitting the Earth every hour, and it's about one cannonball-sized object per hour. So if that were actually the case, we would constantly be getting reports of people being knocked over by invisible objects. So as interesting as that is to imagine, that's definitely not what's actually happening. So, okay. But then again, this is just an analogy. So now we can, go forward and think more about what this means. So it turns out that all we know about dark matter in the region near the Earth is what we call the mass density. What that means is it's the number of the total mass of dark matter in some volume of space. So for example, if I draw a cube of this size, I can say how many kilograms of dark matter would be sitting in that cube. But the problem is that doesn't tell you individually how much each dark matter particle weighs. It tells you basically the product of the weight of an individual dark matter particle times the average number of them. So dark matter could be a few very, very heavy particles or many, many light particles. So in this example, the heavy particles would be like the cannonballs, and the light particles might be something like ping pong balls. And so now I'm going to show you a fun video. Let me just reshare with sound. So indeed, somebody made a ping pong ball barrage machine. So imagine you're standing where this net is. Really, it's not going to be very fun. You know, ping pong balls might hurt a little bit. But if you imagine what's going to happen, they're going to bounce off of you, and they're going to not deposit very much of their energy to you. They're not going to knock you over the same way that the cannonball would. Okay, so what that means is that a human, or an object that's the size of a human, is a good cannonball detector, but it's a bad ping pong ball detector. So the reason is, of course, that the ping pong balls are much, much lighter than you. And the consequence from this is that if you want to detect a particle that you're going to detect by sensing the energy that it deposits to something else in a collision, you want to match the mass or the weight of the particle that you're sensing to the particle that's doing the detecting. So a dark matter detector is going to work best when its mass is similar to the particles of dark matter that it's trying to look for. So again, let's make another analogy with colliding objects. So one example you're very familiar of where objects of similar size tend to collide are billiard balls, right? Imagine breaking a rack of billiard balls with a cue ball. So here in this analogy, dark matter is going to be the cue ball, and then the rack of billiard balls might be like the atomic, the nucleus of some atom. So you know from imagining playing pool that when you fire that cue ball at that rack of other billiard balls, they're all going to break apart, and they're all going to kind of move at roughly the same speed that the original ball was moving at. So the cue ball is transferring most of its kinetic energy to the other billiard balls on the table. And in the same way, dark matter is able to transfer most of its energy to an atomic nucleus if dark matter weighs about as much as an atomic nucleus. So it turns out that actually this is the better mass scale to be talking about. It's true that right now we don't know what the mass of a dark matter particle is, but we have pretty good reasons to believe that it's probably a subatomic particle. So the detector you want to use is not literally a human, it's some detector made of subatomic particles. So the thing that you're looking for dark matter to bump into is some other kind of atomic nucleus. And in fact, this is exactly how some of the most precise detectors for dark matter actually work. So this is a picture from the LZ experiment. It's meant to be a cartoon of a giant tank of liquid xenon. Okay, so xenon is a chemical element. It's what's known as a noble gas, so it doesn't like to react with all kinds of other elements. So helium and argon and krypton and neon are other examples of noble gases. You know, you might know them because they're what are used to make things like neon signs. They have interesting electronic properties. But the point is that you can take these gases and cool them down to low temperatures and then turn them into a liquid. So why would you want to do that? It's because you can pack many, many, many more of the atoms into a smaller and smaller volume of space, and then you increase the number of targets that dark matter has a chance to bump into. So in this case, you see this incoming dark matter particle coming in from the left. It'll bump into some atomic nucleus of a xenon atom. Then the dark matter will leave. You won't see it, but what you'll see instead is that some amount of kinetic energy has been given to that xenon atom in a collision, just like the collision of billiard balls. So then what happens after that is you have some atomic nucleus, which is bouncing around through your detector, and on its way through, it's bumping into other atoms kind of randomly. Each time it bumps into an atom, it might knock loose 1 or 2 electrons. And then you can then collect those electrons in some sort of detector shown at the top of the picture. And that's what you actually see in your experiment. So this is how you detect dark matter going bump in the night. So if it has some force between it and an atomic nucleus, just like the force between you and a cannonball, you can see the effects of dark matter donating its kinetic energy to that atomic nucleus in a collision. Okay, so that's the principle by which one can detect dark matter in an experiment in the laboratory. So there's an issue, which is that all kinds of things are bumping into nuclei all of the time. And one very common example is there's all kinds of particles from outer space known as cosmic rays. They're not quite as exotic as their name might sound, but some particle coming from somewhere in outer space, or maybe the sun, will bump into an atomic nucleus in the atmosphere and then create a shower of other subatomic particles shown in this diagram that will all come down, bump into other stuff, or they might decay and create some other subatomic particles. And they'll create a shower of these very, very high energy particles, including one kind of particularly pesky particle called a muon. So this subatomic particle lives for a very long time. It barely interacts, so it travels through, basically anything, air, rock, whatever. And if it makes it to your detector, it can fake a signal that looks a lot like dark matter. However, this particle does interact with matter. It interacts rarely, but much more often than dark matter does. So what that means is that if I put more and more and more layers of rock between the atmosphere and my detector, the muon will have a higher and higher chance of bumping into some particle before it makes it to my detector and then getting knocked out of the way. So the solution to shield your detector from all these other particles that you don't care about because they're not as interesting to you is to put as much rock on top of your dark matter detector as you possibly can. So this is actually really neat because it means that the best places to look for dark matter are either under mountains or in either active or abandoned mine shafts. So the deepest holes that humanity has drilled that are big enough to put scientific equipment down are mines that were used, for example, to mine gold or nickel. So one example of a scientific laboratory that takes advantage of this abandoned mine shaft is in Lead, South Dakota. So any of you that are fans of Deadwood, the entire show is based around this town in South Dakota called Deadwood, but there's a mining magnate who wants to come in and basically buy up everybody's gold claim and create a mine to mine all the gold that's in the hills. That is actually this mine. So it was started by George Hearst, who's William Randolph Hearst's father, and it was like the largest or the longest actively running gold mine in the US, created like some order one fraction of all the world's gold was mined out of here. But eventually the cost benefit didn't really work out. So the hole in the ground stayed. It wasn't cost effective to fill the hole back with rock. So now you've got a deep hole in the ground. What do? You put some dark matter detectors down there. And actually the same principle was used in this lab in Sudbury in Ontario in Canada. It's actually still an active mine shaft, but there are parts of the mine that are not used anymore for mining ore. And so you can put sensitive dark matter detectors down there. Of course, you can also use a fortuitous situation that nature gives to you. You might have a mountain range that you've already dug a tunnel into, and then you're basically shielded by the height of that mountain range as opposed to the depth below ground. So that's what happens in the Gran Sasso National Laboratory in Italy. So this is a town maybe, I think, 3 hours outside of Rome. It's a skiing town in the winter. There's these really nice mountain ranges, and you put your dark matter detectors right under the mountain, so you don't have to bore deep underground, but you have that benefit of having all that rock that stops all the subatomic particles that you're not interested in. So these are all really neat places. So you can actually go and you can visit the outside of the lab in Gran Sasso. You can in fact drive your car straight through that tunnel. It's just a highway. You have to get permission to take the turnoff to actually go into the lab. I actually was on a road trip this summer and I passed through Lead, South Dakota, and I was able to take a picture in front of the front gate of the lab. Of course, I'm a theorist, not an experimentalist, so I didn't have permission to actually go inside, but my colleagues assured me that it's a pretty interesting place. And I hope to make it to the mine in Canada also. Obviously, travel is kind of suspended due to the pandemic, but hopefully that'll end sometime soon. Okay, so now that I've told you how to look for dark matter, I have to tell you a bit of the depressing news, which is that we've been trying this billiard ball technique for about 30 years, and we've still never seen an unambiguous signal of dark matter. That's unfortunate because we know from that universe selfie that I showed you a couple minutes ago that dark matter is out there in the universe, but we haven't been able to detect it in the laboratory. So what might be going wrong? So one thing is, let's go back to this analogy between ping pong balls and billiard balls. Let's say that you're playing pool and somebody swaps out your cue ball with a ping pong ball. So just picture in your mind for a second what might happen. If you manage to hit the ping pong ball with a cue and even get it going pretty fast, it's just going to bounce right off that rack of billiard balls and it's not going to do anything. So if there's a mismatch between the mass of the cue ball and the mass of the billiard balls, you don't get that efficient transfer of kinetic energy. And that might actually be the case. It might be that dark matter weighs much less than an atomic nucleus. And so looking for those collisions between dark matter and an atomic nucleus are not going to work very well. If that's the case, then what you want to do is look for a particle dark matter can bump into that's as light as possible. So the lightest subatomic particle that's stable and found in ordinary matter is the electron. And so one new technique that can be used to look for dark matter is, instead of looking for dark matter that bumps into the nucleus of an atom, you can look for dark matter that bumps into all the electrons that atom itself is already hosting. So this is basically my job right now, is to design new detectors for lightweight dark matter that's so lightweight that it might have escaped detection in all these other previously running experiments. So unlike the case of bumping into an atomic nucleus, where the recoiling nucleus bounces around and makes lots and lots of electrons, here the best you might be able to do is make a single electron in a macroscopic amount of material. So that's a very, very hard problem. And it's in fact related to a lot of the interest going around with the quantum revolution in science and technology around the world. So the idea of trying to detect a single electron in a block of material goes under the name of quantum sensing. And there's a lot of fun solid state physics that I'm learning a lot about. Despite my training being as a particle physicist, I have to learn how stuff works, where stuff means a block of silicon or some superconducting metal or some other exotic material. And in fact, the weirdness of quantum mechanics means that just because the electron has some mass that you can measure when it's sitting there by itself, if it's embedded in an environment with a whole bunch of other things that it interacts with, there are times that electrons can behave as if they don't weigh anything at all. And that's really interesting because if the name of the game is to try to detect dark matter that weighs less and less and less, you want it to bounce off particles that also weigh less and less. There's only one kind of electron, but depending on the material that it's put in, it can act as if it has different masses. And so trying to look for these materials where the mass of the dark matter and the effective mass of the electron are well matched to one another is kind of an interesting problem in figuring out what's going to be the optimal material out of which to make a dark matter detector. So this is my particular area of research. I think it's really cool because it's ending up being very interdisciplinary. I'm talking to lots of different people all over the university who have different specialties. So with that, let me end the presentation portion of my talk, and I'm happy to take any questions that anybody has.
Well, thanks for that talk. I guess I'll start with one question. In these lightweight dark matter detectors, under what conditions would the materials would have to be? Like, would they have to be super cooled or what?
Yeah, so that's a really good question. So all of these dark matter detectors operate at very low temperatures. So the liquid xenon detector, the low temperature comes, well, first because you have to make the xenon atoms cold enough to coalesce from a gas into a liquid. But in general, if you're at any temperature above absolute zero, you can have occasional thermal fluctuations of the material where an electron will just kind of pop out of an atom just by accident. This doesn't happen in a xenon detector, but it might happen in these more exotic solid state materials. So in general, in addition to having it shielded by all this rock, you want to make it as cold as possible. So there are a number of really interesting techniques that are made to cool things to very, very, very close above absolute zero. And so all of those techniques are brought to bear on this problem with dark matter.
Thanks. We have one question from the YouTube chat. AstroOnTap CU asks, what would a handful of dark matter be like?
So if you literally tried to hold a handful of dark matter in your hand, for your entire lifetime, you would never notice that it was there. There's two reasons for that. So number one is that the average velocity of a dark matter particle is about 200 kilometers per second. So that's about 1,000th of the speed of light, which is pretty slow by light's standards, but it's very, very fast by our standards. So not only are these things whizzing through you very, very fast, the probability of any individual dark matter particle interacting with an atomic nucleus in your body is absurdly low. It's not zero, which has actually led to some really interesting papers about, can dark matter give you cancer? Okay, so the answer is no, dark matter cannot give you cancer, but it's a very interesting thought experiment that, well, look, if this is bumping into atomic nuclei, every once in a while it might, break a strand of DNA and it might create some mutations. And if we know that also ambient radioactivity, even bananas have a tiny amount of radioactive potassium, if you measure the total amount of ambient radioactivity, and then you count up how many average mutations you expect an organism to have over a lifetime, you can bound the probability of dark matter interacting by the fact that we know that that rate can't be much larger than what's already observed. So it's a really interesting thought experiment to try to relate these properties of dark matter in a detector with what dark matter might actually do to you. So obviously, the most interesting scenario might be these macroscopic objects that randomly knock people over. Okay, so that's not the case, but still this idea about thinking of, how might dark matter interact with organic materials? There's actually a proposal to use DNA strands synthesized in the lab as a dark matter detector, precisely because if a dark matter particle comes through and breaks a strand of DNA, we have very, very sensitive ways of knowing where on that strand the break happened. In fact, that's literally how we're doing all these amazing saliva tests right now at Champaign-Urbana. It's PCR, it's the amplification of a certain sequence of base pairs in DNA. And so there's a very creative proposal to kind of use that to know the path of the dark matter as it went through your detector. So that was a very long-winded answer to a very precise question, but it gave me an excuse to talk about a lot of the cool things that I've been thinking about recently. So thanks for bearing with me.
Thanks. Yeah, we're getting a lot of questions, so I'll try and go through them in order. Melanie asks 2 questions. The first is, when you mentioned that liquid cold xenon is used in detectors so that the atoms are close together, why not use a solid material? And then the second question is, what's the most difficult piece of Ikea furniture you've assembled?
Let me answer the second one first. And my epic fail on Ikea furniture was just one of those like hemless bookshelves. My wife was out of town and I had to try to assemble the thing by myself, and I definitely assembled it upside down and backwards, which is not a thing that you should be able to do. So you should have foolproof furniture that does not let itself be assembled upside down and backwards. There's a crack in the bookshelf that's now somewhere in our basement where people can't see it and I can't get embarrassed by it. But that's supposed to be the easy stuff. So anyway, that's why I spend my time thinking about equations rather than holding a wrench. Okay, so then on to the first question, which is why not solid xenon? That's a fantastic question. And actually, I've been thinking a little bit about what advantage you might get by having a solid rather than a liquid. So part of the issue is that it's much more expensive to cool things. And you don't need xenon to be that cold to make it a liquid, but you need it to be very cold to make it a solid. So, just for kind of cost-effective reasons alone, if you can get away with doing it as a liquid, the average distance between the atoms is not that different between a liquid and a solid. So you don't actually gain that much. And then the other reason is that there might be properties of the liquid phase that are conducive to the kind of thing that you want to detect. So maybe you can measure very precisely the average number of electrons that are created as a nucleus is going around and bumping into other atoms. That might be harder to do in a solid because kind of all of the other atoms are trapped in place. So those are details that I'm definitely not an expert on, but those are kind of some of the considerations that might go into doing this. But in general, you want the most atoms you can pack into some volume. And so in general, solids and liquids are better than gases.
Question from Anthony. Why is dark matter useful to study? Which questions does it help answer?
That is an excellent question. So let me now go back to this selfie picture. So if you buy that this picture represents the early state of the universe, so that tells us something about when the dark matter had to exist. It had to already be there by this 380,000 years after the Big Bang, because it had to have the interactions with other gravitational interactions with other particles that made these characteristic size of these hot and cold spots. So knowing something about dark matter, knowing that it was there in the early universe, tells you something about the dynamics of the early universe from its very first moments. And then you might have to ask, okay, well, we know on average by, for example, measuring the motions of stars that are near us, how much dark matter there is near us. How do I relate that number, how much dark matter there is today, to how much dark matter there was back then when the selfie was taken? And so understanding that transition between a very, very long time ago and today tells you something about how dark matter interacted with all the other particles in the universe. And so basically it lets you kind of do universe archaeology. It lets you rewind the clock further and further back, understanding what happened at even earlier moments in the evolution of the universe.
There's 2 questions that are similar, one from Nick and one from James. Do we know if dark matter is found in clumps or more spread out in the universe? And then how do we know that dark matter moves through space rather than just sitting in large mass units at the center of each galaxy?
Great. So those are actually really related questions, so I can answer them both at the same time. So let's imagine now running the movie forward. So I have, dark matter in the universe. It's kind of spread out spatially, roughly evenly. But what these hot and cold spots are telling me is that the universe is starting to clump. So if I move the tape forward, each of these kind of hot spots and cold spots will eventually attract more and more matter around it, because gravity attracts. So I have stuff here, then it likes to pull in other matter, and stuff gets pulled and pulled and pulled in. it turns out that on average, there's more dark matter in the universe than ordinary matter. And so a really beautiful picture is that dark matter is the scaffolding, the gravitational scaffolding by which galaxies are formed. So dark matter starts to clump, and then ordinary matter clumps around it. And then that clumping is what allows stars to form, and then allows galaxies to form, and eventually our sun, and then planets, and then us. And so in a very beautiful sense, we would not be here but for dark matter. Okay, so then, if you look on a very micro scale, on average, dark matter is pretty smoothly spread out, but on a macro scale, it tends to be clumped around galaxies. So why is it not all sitting at the center of the galaxy? It's basically the same reason that not all of the mass in our Milky Way galaxy is sitting at the center, but it's kind of spread out in these spiral arms as the galaxy rotates. If you try to collapse something that is spinning even a little bit, there's a principle in physics known as conservation of angular momentum, which means that you can't have the mass collapse entirely to the center and sit there. It basically has to preserve its rotational velocity, and so it keeps spinning around. And so in that sense, dark matter is moving around the galaxy in kind of these random trajectories, but it can't all collapse to the center because it has some velocity that it can't get rid of. And so the picture you should have in mind is that if you look at a photograph of a galaxy, like something from the Hubble Space Telescope, there's the visible mass you can see that, let's say it extends out to here, and then out to a much, much, much larger radius is this cloud of dark matter that you can't see, but you can infer its effects from looking at the gravitational dynamics of that system.
We have 2 more questions, which are similar. Would understanding the nature of dark matter change how we understand gravity/gravitons and gravitational waves, a la LIGO? And then another one about gravity. Can dark matter form black holes?
Okay, so let me answer the second one first. Just like any amount of matter, if you pack it into a small enough space, it can form a black hole. So certainly you can have black holes that are originally formed from dark matter. Once it becomes a black hole, you don't know what caused it to form. So actually, we still don't quite know what is responsible for the black hole that's sitting at the center of our galaxy. It could be that some portion of that came from dark matter falling in, then also some ordinary matter, and then eventually a black hole was made. So certainly that can happen. Sorry, remind me what do we learn about gravity from dark matter? So the unfortunate answer, as far as I understand it, is not too much. That in some sense, gravity was a hypothesis that went into defining what I meant by dark matter. I'm defining dark matter by something that feels the force of gravity. And so I'm kind of, by restricting the problem like that, I'm not imagining that dark matter is modifying gravity in really any interesting way. Then you might ask, okay, could you sense dark matter by its effect on gravitational waves as seen by LIGO? Yes, that's certainly a possibility. But in that sense, you're not really learning as much about gravity as you are learning about dark matter through gravity. And actually, in some sense, that's a nightmare scenario that all of us dark matter theorists have to worry about. It's in principle possible that the only force by which dark matter interacts with anything is gravity. In that sense, it would never bump into a nucleus. So the force between dark matter and a nucleus that I was imagining here is something like the weak nuclear force, where at small enough scales, nuclei act like billiard balls. But the gravitational force between 2 atomic nuclei is just so absurdly small as to be totally negligible. And if that's the case, it would be really hard to detect dark matter because it would never deposit all that energy in a collision. So some of my colleagues are thinking about really interesting ways using levitated microspheres, like an array of tiny, tiny spheres that are like microns in diameter that are levitated that will all kind of slosh back and forth together as dark matter passes and its gravitational effects are felt. Those are really interesting futuristic ideas, but those detection principles are actually much farther away. So I hope that dark matter has interactions other than gravity, but if it doesn't, hopefully we'll learn that because none of these experiments will show any results in the next 20 years, and then we can move on to thinking about how we detect dark matter that only interacts with gravity.
Alex asks, can you design multiple different types of detectors to constrain specific dark matter parameters or particles? And also, what's the coolest material you've learned about since diving into material science?
Yeah, those are awesome questions. So certainly there is no one-size-fits-all solution for dark matter. And the biggest reason is that we don't know what the mass of a dark matter particle is. So we should try to design as many detectors as we can that are each optimally matched to some range of possible dark matter masses. So I thought about a whole bunch of different materials. So by way of answering the second question, there are these things called Dirac materials where, let me actually go to the picture that shows that. So the materials where electrons interact as if they don't have any mass are extremely cool. And these are, one example of a material like that is called graphene. And so you might have heard about this because it won the Nobel Prize several years ago, but actually the people who discovered it also won the Ig Nobel Prize. I think that is a unique statement in the history of these prizes. So what they did is they took basically pencil flakes. So if you rub a pencil on a piece of paper, that tip of the pencil is made of graphite, which is carbon atoms that are kind of randomly arranged in sheets. If you exfoliate it by putting a piece of Scotch tape on that paper, isolating a tiny sample, pulling it off, and then repeating, eventually you get to a layer of carbon that is 1 atom thick. And that's known as graphene. And that material has the property by which electrons basically act as if they don't have any mass. So the problem is to get enough carbon atoms to see anything with a material that's 1 atom thick, you're going to have an absurd surface area of this material that covers multiple football fields. So I've written papers about this. It's not very practical. So it turns out there are bulk materials that are not like 1 atom thick, but actually exist in all 3 dimensions that also have this electronic property. And I'm working with a number of professors at Illinois and other places to synthesize these materials and turn them into dark matter detectors.
All right, I have a question. In these detectors, you could detect the presence of dark matter, but could you also learn information about the origin of these particles, where they're coming from in the sky?
That is an excellent question. So the buzzword by which that goes by in my field is directional detection. So you'd like a detector that has a different response if the dark matter is coming this way versus this way. So actually that graphene example is a really nice example of that. So it turns out that the properties of quantum mechanics tell you that if your dark matter is incident on a sheet of carbon atoms from this direction, and you knock out an electron, it prefers to go the same direction the dark matter was going. Okay, that sounds pretty intuitive, but you can calculate it exactly using quantum mechanics, and that's the answer you get. So if you imagine the Earth rotating over 24 hours, so dark matter is kind of like a wind that's coming at us, and as the Earth rotates, the direction of that wind with respect to your detector changes over a day. And so if you have a detector that sees more electrons that go this way versus that way, then over the course of 24 hours, the signal you see in your detector will change. And that is precisely the signature of which direction the dark matter is coming from. And that's a really interesting quantity to measure, because how did dark matter acquire those velocities in the first place? Well, we think it did because of the dynamics of how our galaxy formed by a bunch of stuff falling into our galaxy, colliding with things, stripping off mass from other galaxies. And that process of formation of our galaxy is something that dark matter might actually be able to probe. We could do galactic archaeology if we knew the direction that dark matter was coming from. So first we have to see a signal, but then if we see a signal, having a directional detector is extremely powerful.
Thanks. This is from Akshat. Are dark matter particles their own antiparticle? If so, can you see its signature near a black hole?
Good. So we don't actually know whether dark matter is its own antiparticle. I think most detectors don't rely crucially on whether or not it is. There can be different, if dark matter was an unstable particle and could decay into other kinds of particles, then that might be something that you would be able to see at a detector. Trying to see the signature of individual dark matter particles around black holes is hard because we really don't have a permanent window on any one black hole in particular. So there's a black hole at the center of our galaxy, but there's all kinds of violent stuff happening around it. We also see black holes from, for example, the LIGO detector, but we only see them for a brief period of time, and we can't really localize them very well in the sky quite yet. So there might be interesting signatures of dark matter around black holes, but first it would require us to really be able to pinpoint a number of black holes in the universe and study them for a long time.
Are neutrinos possible dark matter candidates? If so, how are they different from particles you are trying to observe?
Again, it's an awesome question. So for the existence of dark matter was, let's say, unambiguously established in, let's say, the 1980s. And at that time, it was certainly a possibility that neutrinos could make up all of dark matter. The problem is that neutrinos are too light and they move too fast. What that means is that if you track the evolution of dark matter in the early universe, neutrinos don't weigh enough to clump as much as we see dark matter doing. So they might be able to make up a fraction of the matter in the universe that doesn't interact with light, so dark by my definition, but they can't make up the bulk of the stuff that's responsible for all of that clumping process. And indeed, neutrinos pose a background to all of these dark matter experiments at some level, because they move pretty fast, they're basically invisible, and they collide with atomic nuclei. So one way in which looking for dark matter scattering off of electrons has advantages over looking for dark matter scattering off of a nucleus is that neutrinos don't like to interact with electrons as much as they like to interact with nuclei. So you might hope that actually there's less of these background processes that pollute your detector from neutrinos if you're looking for electrons versus nuclei. But it's a problem that all the detector people have to deal with.
There's a question asking to explain a little bit more about the experiments in the caves. So maybe you could talk about the depths of these experiments, sizes of detectors.
Sure. So going back to these pictures, actually the picture of the Homestead Mine is a little bit misleading because the lab is not actually in that giant hole, but the depth is about correct. So both Homestead and the Vale Mine in Sudbury are about 2 kilometers deep, so about 8,000 feet. Those are some of the deepest holes ever drilled by humanity. And we would prefer to go as deep as possible. At some point, you run into problems because the Earth's mantle is the core of the Earth is both hot and radioactive. So you don't want to go too deep, but no science agency has the money to dig another hole. So you take whatever hole somebody's already dug for you and you do the best you can. And so there are tunnels off of the main mine shaft that have been drilled and then created as clean environments with basically very, very little pollution of any kind. So I haven't actually been down to the mine in Canada, but what I understand is that basically you get down there, you take a shower after taking this elevator that goes down 8,000 feet in an absurdly short amount of time. They actually turn down the speed for the non-miners just because the pressure in your ears is kind of uncomfortable if you've never done it before. So you shower, you put on these bunny suits, these like clean room clothes, because you don't want any kind of spurious particles from your clothes from the outside to get into the detectors. And then what you see is basically what looks like a pristine clean room in this mine shaft deep under the earth. So the sizes of the detectors, I was actually in Gran Sasso and I saw the xenon detector. It's like, maybe 20-ish feet high and I don't know, maybe I'm probably gonna guess wrong, like 15 feet in diameter or something. So it's not like lecture hall sized, but it's pretty big. But one thing that's actually interesting is that the materials that I'm looking at now, as your dark matter gets lighter and lighter, the number of dark matter particles, right, because the mass density is fixed, gets larger and larger. And so you actually can get away with smaller and smaller detectors to look for this lightweight dark matter. The kinds of prototypes that I'm looking at and the detectors that are currently running are you can fit in your hand. They're little bits of silicon that are about this big. Maybe at most they'll be like 10 kilograms, the mass of a small bowling ball, but those will be kind of tabletop size detectors.
Is it possible that what we think of as dark matter is actually multiple different types of particles? And is it even necessarily a particle? Could it be something else, like a wave?
Yes. So the answer to all of those questions is yes. So certainly dark matter could be made of multiple kinds of particles. We have to take the minimal assumption just to get started, because once you know how to look for one kind of dark matter, then you can imagine that dark matter is a composition of different kinds, and you can have multiple experiments running simultaneously to look for all those kinds of dark matter at once. So that's basically the motivation for having a program of many different kinds of experiments that are all running at the same time. And in fact, if dark matter, so in quantum mechanics, everything is either a wave or a particle depending on what question you ask it. So the question you might want to ask dark matter is, does it act like it's bumping into individual atoms, or does it act coherently over the entire detector, kind of oscillating everything together? So if your dark matter is about, let's see, try to get the number right, about 1/1,000,000th of the mass of the electron or lighter, then it actually behaves more like a wave than a particle. And there are detectors that look for wave-like dark matter by looking for very, very tiny electric and magnetic fields that are created by those dark matter particles. Those are a totally different kind of experiment. They don't use this billiard ball technique. I'd be happy to talk more about it. If you want to send me an email afterwards, I'd be happy to give you some more details. But those are also really interesting. And they're another example of, well, we don't know exactly what we're looking for, so we should look for everything.
Another question is dark matter related to dark energy?
Again, a really good question. I don't know the answer. At this point, there is no compelling reason to think that these things have a one-to-one relationship. There are lots of really interesting ideas about how they might be related. In the universe as a whole, the way that I think about it is that if you think about the mass density of the universe, so the density in stuff that can reasonably be called particle-like, then dark matter makes up 85% of the mass density of the universe. But if you talk about the energy density of the universe, dark energy is like the energy of empty space. And that's like 60% of the energy budget of the universe. Dark matter is only 25% of that energy budget. So of things that feel the force of gravity and attract gravitationally the way that ordinary particles do, there's a lot more dark matter than ordinary matter. But if you think about just anything that carries any kind of energy whatsoever, including empty space, then dark energy wins.
As to when we'll discover a dark matter particle, a year within our lifetimes, longer?
So I'm working on this because I think this is the biggest problem in physics that I personally have a chance of knowing the answer to in my scientific lifetime. So I am optimistic that we will detect dark matter in my lifetime. I think I'm, if I were to put a number at it, I'm more confident that we will know whether or not dark matter can have interactions other than gravity in my lifetime. Of course, if all these experiments see no positive signals, that might be a signature of the fact that dark matter has no interactions other than gravity. Then that means you have to do a whole bunch of other kinds of experiments. And what we're doing right now is ruling out one by one all the possibilities by which dark matter might have non-gravitational interactions. Once we've reached the end of that list, at least in some reasonable categorization, then we can move on to this other hypothesis. So I'm pretty optimistic. We're going to have to see how these experiments turn
out. Another question, what do you think dark matter is, in your opinion? So I guess maybe how does it interact? Typical masses?
Yeah. So the way that I would answer that question is by using a concept from statistics called Bayesian inference. So there's the idea that if asked a question like that, I have to give some sort of probability of what I think a dark matter particle is made of. And that probability might be my own personal inclinations and biases, but every time a new experiment comes out with a new result, I have to adjust those probabilities based on that new result. This is the canonical example in medicine is like, if a test has a certain false positive rate and a disease has a certain incidence in the population and you get a positive test, what's the probability that you have the disease? So the calculation starts by the probability that somebody in the population had the disease in the first place, and then the new information is a positive test, and that adjusts your probabilities. So let's say I started out, maybe right when I was born, I didn't know anything about physics. All dark matter candidates are equally likely. Okay, so then there are a lot of interesting theories that tie dark matter to other problems in physics. There's a particle called the axion, which solves another problem in nuclear physics. There's particles called WIMPs, which solve a problem in particle physics that's related to supersymmetry. And these are all really good ideas. So let's say that maybe my probabilities for both of those are 50%. So it's either one particle or the other. Well, okay, now we've been looking for 30 years for dark matter. We haven't seen any of them. And then the reasons for thinking about dark matter that is related to supersymmetry were already tested at some level at the particle collider, which is the Large Hadron Collider in Switzerland. That experiment has not seen any evidence for dark matter, nor any of the other particles that might come along with the supersymmetric dark matter, these WIMP particles. So now I might say my probability on that has gone down a little bit, but all probabilities have to add to one. So I have to, increase my probability of some other kind of random amount of dark matter somewhere else. So if you're familiar with the jargon, I might say that maybe there's a 30% probability that dark matter is made of axions. There's a 30% probability that it's made of dark matter that's lighter than the proton mass, and a 40% probability that it only interacts gravitationally and we'll never see it in these experiments. So I'm not willing to put a monetary bet on that, but that's kind of roughly where I stand at this point.
Thanks. I think this was in your first slide. You showed that there's kind of these differences in temperature across the sky. What are the variations in temperature that we see?
Good. So it's actually given on that scale that's at the bottom of the plot. So the variations in temperature on the orders of hundreds of microkelvin. So the temperature of the photons by the time they've reached us today is about 3 Kelvin or 3 degrees above absolute zero. And so the variations are on the order of 1 part in 10,000 of that. So the universe as a whole is extremely homogeneous. That was a really interesting observation at all. Like, how does this part of the universe compare to the part that's diametrically opposite? How do they know to have the same temperature? And that's related to the theory of inflation. But the fact that we can measure these precise differences is really interesting, and that's what gives us information about dark matter. So actually, the magnitude of the temperature fluctuations also gives you information about what was going on in the early universe.
Does dark matter relate to sterile neutrinos?
Good. So for those of you that are not maybe so familiar with the jargon, so a neutrino is a subatomic particle that, as I mentioned earlier, barely interacts with anything. A sterile neutrino is a hypothetical new kind of neutrino that interacts with even fewer things. So basically, all it does is potentially interact with atomic nuclei, and then only through gravity elsewhere. So that is another way of giving a name to what dark matter might be. So a possible particle physics identity or candidate for dark matter might be sterile neutrinos. There are ways of looking for them in telescope experiments. There are ways of looking for them in experiments on Earth. I haven't worked on any of them myself, but the jury is still out. That's definitely one possibility for what dark matter could be.
Another one. So what happened before the Big Bang? Can we know it? And if so, what can dark matter tell us about what happened before?
Good. So in some sense, one has to define one's domain of validity for a theory. The kind of traditional cosmologists will say that the universe begins at the Big Bang, and before that, by definition, my equations don't make sense. So I can't study there because any answer that I ask it will come out with nonsense. There's a slightly more refined way of explaining that, which is that there's some period of time where the universe underwent this period of exponential expansion called inflation, and then after that era ended, all of the energy in the expanding universe was dumped into creating particles, and that's what we call the Big Bang. So in some sense, the fact that the universe is so homogeneous as a whole is evidence for the theory of inflation, which is one example of what might have happened before the Big Bang. If you define the Big Bang as the production of actual particles as opposed to just the universe expanding really, really fast. That, of course, then begs the question, okay, so what happened before inflation? And then once again, we're in this domain of validity issue where we're not really sure how to make sense of any equations because you kind of set your initial conditions as the beginning of this process. Okay, so what can dark matter tell us about this? Unfortunately, not too much, precisely because the Big Bang kind of erases all information on what came before it, with the exception of these tiny temperature fluctuations are related to the quantum mechanics of what was going on in this expanding universe during inflation. Unless you got very lucky and dark matter happened to be intimately related to whatever process was driving that exponential expansion, those are kind of two logically separate things. And so the Big Bang doesn't tell us so much about dark matter, because if the universe was, after the Big Bang, was at a hot enough temperature, any particle that was sufficiently light could be produced, including dark matter. So some of my colleagues at U of I think about the relationship between dark matter and inflation. This is not my area of expertise, and there's some really interesting models by which these things could be related, I'll say that they're not necessarily related, but if we saw a positive detection of dark matter, of course we would study it to death, and probably we'd be able to learn something about inflation in the Big Bang.
Well, thanks very much for all those answers. Those were some pretty good questions. Oh, here's another one just coming in. So this is from Alex. What's the difference between cold dark matter, and I guess he meant hot dark matter, which is more likely?
Good. So a neutrino is an example of what we call warm dark matter. And by warm, cold, and hot, I'm not talking about the photon temperature anymore. I'm talking about the average velocity of the dark matter particles. So if they're moving very, very fast, I'll call them hot. If they're moving not so fast, I'll call them cold. So dark matter particles have to be slow or cold enough in the early universe to form these gravitational clumps. And so we know that most of the dark matter in the universe has to be cold in that sense for the clumps to have formed the way they did, and then for galaxies to have formed on top of them to get the right amount of galaxies that we see in the universe and the right sizes and so on. So some component of the dark matter might have also been moving fast when it was created. You can look for that in experiments, but it won't be the dominant form of dark matter today. That's at least something about the dark matter, and that's one of the things that we can say with pretty good confidence.
Does anyone have any final questions in the YouTube chat? Maybe just give it a little bit more for people to type. I know sometimes it takes a while to type long questions. Nicholas asks, what are you drinking?
A rye Manhattan, which I've now finished most of except for the maraschino cherry. And so for those of you keeping score at home, always get the real maraschino cherries, none of that radioactive red stuff. So these are the Luxardo cherries. And once again, I hope to be able to join you at an actual bar for Astronomy on Tap when this pandemic is over. Because it's a lot more fun to have these discussions in person. So, thanks so much for bearing with this very Zoomified format.
Yeah, thanks everyone for all the questions. They were really good, prompted a lot of discussion, and thank you, Professor Yoni Kahn. Really nice talk.
Thanks, a lot of fun.